for this problem. I have Newton's law. I have a spring. I know the spring constant K. And I know my mass. I know my spring constant K. So I can compute this A. Because I compute from K, from spring constant, K, and system mass M. Then I compute AC. Right? Then and delta T, I compute A. Right? Agree? That's my A. That's my A come from. That's my A come from, right? Agree? If I give you a problem, I say, here's the problem. And I say, you design an observer for me. How can you do that? If I give you this spring problem, then I give you mass M, I give you the spring K, then I say, okay, design an observer for me. Design a state estimator for me. I tell you that my U, where's locating my U, then I can know the B, right? And I tell you where I measure my quantities. Then I can know this. Agree? Well, you got to know how to apply this, right? You don't want to know only the mathematical equation here. You got to realize, how can I apply this? How can I have A, B, C, D? If I tell you, hey, this is the building, how can I compute A, B, C, D with this building? You have some analytical way to do it. Agree? So, for this problem, because I come from the spring constant, I come from the mass, and I have AC, and I give you delta T, and I can compute A, and I give you where the input are, where the input is, then I compute B. I tell you where I measure, I compute C and D, right? And then I have to figure out how much G I need to get into the observer. Okay, so if I give you a problem, I go, here's the system. Design observer for me. That's one of the problems. Maybe good for midterm problem too. And that is, now I'm talking here. All right. So, system matrix now is, we know that. That's my system matrix. Because I give you delta T, I give the spring constant, I give you mass, then I give the input location, I give my measurement is the accelerations. Because I have acceleration, so I have a D term here. I have C and D. I agree? Now, initial condition and time response. I say my initial condition is 1, 1. I have a system. I'm going to excite it. I have a transient response because I have initial conditions. My U is 1, minus 1, 1, minus 1, and 0, 0. And I excited, my solution is this. X1, I have X1 equal to AX0 plus UBU0 and equal to you sub A in there and B in there and EU in there, then X1 is 2, 0. I have Y2 equal to minus 1, 3. I have X3, I have X3, X2. And X3 is 2, minus 2 and 2. And X4 is 1, 1. And my Y0, if you sub into there, Y0 equal to 0. Y1 equal to minus 3. Y2 is 2. And Y3 is equal to 1. That's my output measurement. That's my measurement. My measurement is, I have acceleration measurement. This is my acceleration measurement. Y at 0, acceleration is 0. Y at 1, acceleration is minus 3. Y2, acceleration is 2, y3 acceleration is 1. Okay, that's my measure. That's what when I do experiments, that's what I got. All right. Now, in real system, you gotta go to your lab to measure. Now, this is just, I just do simulation for you, show you the power of observer. So, giving you the output y0, y1, y2, y3, that's given. And I don't know anything else. All right? How can I do estimations? So my G is equal to 0 minus 1. That's my G. I didn't show you how to design G yet. Now, assume my estimate initial condition is 0, 0. That's my estimate. Can I do that? Because I don't know initial conditions. Theory, I don't know initial conditions. I just know my output. I know my input. I might know my output. That's what I know. Right? So, I know the input. I know the output. I don't know anything else. That's all I know. Of course, now I assume I know A, B, C, D here, and G. Assume you know A, B, C, D, and G. The A, B, C, D, you compute it from your system. The G, I will show you how to do that later. Okay. Now, this is my solution. Now, y hat equal to cx hat 0 plus du hat, then y hat 0 equal to 1. But my real y is 0. That's my real y. Okay? My y hat, this y hat is cx hat plus du. Sorry about this. This is not the in the screen. The hat is missing. Your notes, the hat should be there. All right, right. You see the note? Anybody got note? The note is correct. All right, right. Okay. So, if you look at this carefully, you find out my y hat 0 equal to cx hat 0 plus du 0, that equal to 1. But that is not equal to y to y0, my measurement y0, that's supposed to be 0. Agree? Now, my y hat 1 equal to cx hat 1 plus du 1. That equal to how much? You can look at that, or plus. So I need to plus du plus plus du. Need to x. Now I go to x hat 1 equal to ax hat 0 plus bu 0 plus g, then y hat 0 minus y1 y0, and that equal to 1 0. Alright? So, if I do that, my y hat 1 equal to cx hat 1 plus du1, then that equal to minus 2. And my real y is 3. Minus 3. y1. Right? So, my estimated y hat is not equal to my real y0, my measurement y0. The estimate y1, that is not equal to my true measurement y1. If you look at yx hat 2, you look at from the screen there, that equal to -1 and -3. My y hat 2 equal to cx hat 2 plus du2, then that is equal to 2. How about my y2? My y2 also equal to 2. Equal. Alright. So my first estimate of y hat 1, y hat 0, not correct. My step, the next step, y hat 1 equal to -2, but the 2 is -3, so it's not correct either. But my second step, the y hat 2 equal to cx hat 2, then equal to 2, then that's the same as your measurement. So from this on, y hat 3, it will be equal to y2 3, and y hat 4 will equal to 2y4, and so on. They're all true now. So only two steps. Those are not the same as your true measurement. That one and that one. After that, it's all become the same as yours. So it doesn't matter your initial conditions. Now, my initial condition, my estimate initial condition, I assume x hat 0 equals 0, 0. That's 0, 0. I assume, because I don't know. Now, you can assume any number, any value. For example, I assume x hat 0 equal to 100. Right. So, this initial condition here, I need to explain to you, this is important concept here. Now, x hat 0 for this one is equal to 0, 0. Then we know that my x hat 0 won't be equal to real x 0. Alright?